Hello dear my friends, welcome to this discussion. We are going to be looking at Fourier transforms. So you realize that a Fourier series works with periodic functions or signals. And what about when we don't have periodic signals, and which is actually in most real world signals? If it is not periodic, so what about aperiodic signals? So that's where the power of a Fourier transform comes in, because it is easier to analyze a signal by manipulating its amplitude and frequencies. But what if a signal is not periodic and you cannot tell its frequency? So the Fourier transform comes in to transform this signal from time domain. So Fourier transform does transform or changes the signal from time, space, etc. domain to frequency domain. Once we have the frequency domain, then we can manipulate the signal and be able to tell the response of the system. Now, a Fourier series can be represented in the form of a complex form, because the complex form is actually what can represent the signal in the form of its amplitude and frequency. So we can see that if you have a function f of t, this can be represented as sum from n is equal to negative infinity up to infinity of Cn x exponential of j2 pi n f naught, whereby f naught is 1 out of t, and this is called the fundamental frequency. And then Cn itself is actually like the amplitude. So this Cn is the Fourier coefficient here, which is going to be representing like the amplitudes, and then it is actually equivalent to 1 out of t, integrating from negative t out of 2 to t out of 2 of x of t exponential of negative j2 pi f naught n t with respect to t. So when you look at this, first of all, this Euler number ej, for example, ej theta, remember is the same as sine. Let us take cos theta plus j sine theta. So this is the polar form of the complex relationship or the complex number. So meaning if I bring this into here, then it takes me back to the other component of f, for example, f of t equivalent to a naught plus sum from n is equal to 1 up to infinity of maybe a n cos n pi x, okay, this is t out of r plus sum from n is equal to 1 up to infinity of b sub n sine n pi t out of r. You can see it has some relationship or some resemblance. So for that matter, once we break down this into this form, Euler form, and we take it into a complex form, then we can still be able to visualize the issues of frequency and then the amplitude. So meaning if this is a Fourier series, if it is for a periodic function, then we are able to analyze this signal. So if it is not really a periodic signal, then we need to talk about a Fourier transform. So for a periodic signals, where we needed to change from time domain, space domain to frequency, because it is easier to work with the frequency. Because you can manipulate frequency and then be able to see the response of the system. You can look at the frequencies and say these frequencies are desired or desirable, these ones are not desirable. That's why you need to do a transformation from those other domains to frequency domain. So what is the Fourier transform looking like? So first of all, we are going to first do note number one. We are going to be considering what happens when period t tends to infinity. When you look at this here, the fundamental frequency is equal to 1 out of period. But now let's look at what happens. Here is, so let's look at, consider what happens when the period t tends to infinity. So you will see that the function is no longer periodic. Why? Because the fundamental frequency f naught equivalent to 1 out of t has gone to 0, because 1 out of infinity is equal to 0. Now, if it tends to 0, now the discrete set of frequencies, that's discrete set of frequencies in f naught, okay, will no longer be discrete, but they will become continuous. In other words, we are saying if now this is if we are talking about a Fourier series, we had discrete frequencies, but when we transformed it, okay, when we tested it as t, this period goes to infinity, it is no longer going to be periodic. The fundamental frequency is going to 0, and we are no longer going to have discrete frequencies. We are talking about something like this. Frequencies that are discrete are in this form. So it now changes to frequencies that are continuous. Here, discrete, we have continuous frequency. So therefore, point number 5, the Fourier coefficient Cn, the Fourier coefficient Cn transforms into a continuous function. So it becomes a continuous function x of f. So this becomes a transform. So if we are to use the definition, using the definition of Cn, we can replace the summation with integral by saying now, therefore, that x of f is going to equal to, remember we had 1 out of t integrating, so we shall have cross multiply and we'll have tcn. So this shall be taken as a limit as t tends to infinity. This becomes now integral from negative infinity to infinity of x of t exponential of negative j 2 pi f of t dt. So this frequency is no longer a set of discrete values, but it now becomes a continuous value or a continuous variable. So what does that tell us? This actually becomes x of f equivalent to integrating from negative infinity to infinity x of t exponential of negative j 2 pi ft with respect to t becomes the Fourier transform. So we are going to transform this x of t from the t domain or time domain to the frequency domain. So for a general function x of t, then that general function x of t, its Fourier transform is going to be defined by this integral. And now the inverse inverse Fourier transform gives the function back, the function x of t. So here we are saying the Fourier transform of x of t is equal to integrating from negative infinity to infinity x of t exponential of negative j 2 pi f of t with respect to t. Then the inverse, this is actually x of f. So the inverse of x of f will now become x of t, which is equivalent to integrating from negative infinity to infinity of x of f exponential of j2 pi, this is ft with respect to f. So you have to mind about the difference between here, this component here and the component there. So key observations, one is that in the Fourier series, frequencies are discrete. That is n f naught, because we are saying at a different value of n, we have a different value of n f naught, that is frequency. At a different value of n, we have a different value of n f naught. So that means the frequencies are going to be discrete. And with while in Fourier transforms, the frequencies are continuous. That is one point. Another point is that Fourier series applies to periodic functions, applies to periodic signals, while the Fourier transform applies to aperiodic signals. We have again seen that as t tends to infinity, the discrete spectrum of the Fourier series turns into the continuous spectrum of the Fourier transform. So let's take an example. Take an example of a wave function. So we have a function f of t equivalent to a, okay, for t between negative t out of 2 and t out of 2, whereby it is the period of the function, and then 0 ls. So let's look at the Fourier transform of the function. So we'll begin by noting another form of a Fourier transform, f omega, because this also represents a Fourier transform, but in omega, in terms of angular frequency, which is also directly related to frequency. So this is equal to integrating from negative infinity to infinity of f of t exponential of negative j omega t with respect to. So now let's proceed and put in our function f of t. So the Fourier transform will become integrating, actually now it becomes from negative t out of 2 to t out of 2, because this range or interval is the same as negative t out of 2 less or equal to t less or equal to t out of 2. That's what it means. So we are going to integrate from negative t out of 2 to t out of 2 and of a, okay? Then exponential, this is supposed to be negative omega t with respect to. So meaning f omega will become a, then integrating from negative t out of 2 to t out of 2 of exponential negative j omega t with respect to t. Now what is this going to give? This is going to give us a, then exponential negative j omega t divided by negative j omega from negative t out of 2 to t out of 2. So f omega, or the Fourier transform, becomes a, and let's now start substituting in our limits. So this becomes negative exponential negative j omega t out of 2, Then we are taking away exponential of negative j omega, then negative t out of 2. Then we are dividing everything by negative j omega. Let's proceed. So the Fourier transform becomes a into, so we have exponential negative j omega t out of 2 minus exponential of j, this positive and that, this negative and that negative cancel, and we get a positive. So this becomes j omega t out of 2 divided by negative j omega. And let's do some manipulation here. From the Euler identity, that sine theta is equal to actually 2j sine theta is equal to exponential of j theta minus exponential of negative j theta. So what does that call us to do? We do some little manipulation here, and then this becomes like, so f omega becomes a into, let's put the negative outside and we bring exponential j omega t out of 2 minus negative j omega t out of 2. Then we put this out of negative j omega, and then the negatives will cancel. So what does this mean? Whenever I have this, I put 2j sine something. So f omega becomes what? A into, this is going to be 2j sine of what? Sine of w or omega t out of 2. Then we are dividing this by j omega. So meaning this and that will go. And then what becomes the Fourier transform? So the Fourier transform, f omega becomes a. So let's do much more manipulation here so that we have, we are going to have this a. Let us assume we have a times t divided by t out of 2 omega into sine omega t out of 2. So this obviously gives us something like a, okay, t times sine omega t out of 2 divided by t out of 2 times omega. This is the Fourier transform. The moment I look at such a function, it reminds me of sine, okay, sinc of x. I mean, a sinc of x is equal to sine of x out of x. So meaning f omega will equal to a t times what? Times the sinc. This is a sinc function. So whenever there is there is x, I put wt out of 2. So this becomes wt out of 2. So finally, the Fourier transform of the wave equation given above is fw or f omega, that is angular frequency. At is equal to at times sin of omega t out of 2. So we have moved it from the time domain. Remember, it was in f of t. This equation was in f of t. And then we have taken it to frequency domain. So I hope you have gotten at least a hint on Fourier series transformed into Fourier transform. And what does the Fourier transform do? The Fourier transform transforms from a signal from spatial time domain to frequency domain, and then it becomes easier to analyze.